Hi, this is a video about electron configurations. So the quantum model allows us to kind of describe it's like kind of giving an address of where the electrons are likely to be found. We don't know exactly where they are, but we can be pretty highly probable that they're in certain areas. I don't know if you guys watched the movies or read the books for Harry Potter, but the Marauders map, you know how like he'd be able to see Snape's feet or, someone Dumbledore walking over here. That's kind of what it's my little analogy to electron configurations. It's like we're saying, well, they're over here in the castle and then they're here and so on. So anyways, let me get to the real thing. And let me make this a little bit easier to see. So electron configuration, you may have had this as ninth graders in honors. If you did have honors, don't worry if you've never seen it. I'm going to teach it like you've never seen it. And even in ninth grade, if you did do it, you may or may not have understood it quite as well as I think you will now. So electron configuration is when we write a number. So we would write a number in front of a letter. This number is really the principal quantum number. So in this case, we're talking about n equals 1, or the first energy level away from the nucleus. The superscripts, those are the number of electrons in that first energy level in the S sublevel. So this is really the sub level, which remember that was based on the quantum number, the angular quantum number. So there's a few rules about electron configurations that I want to cover. One of them is the Pauli exclusion principle. It's also related directly to the fourth quantum number, the spin. So I have an analogy again, like a couch. So on a couch, you could have no one, you could have one person, or you could have two people. But if you do have two people, they have to be upside down. So what does that really mean? I know it seems silly. An orbital, the couch is the orbital, and on paper, we use a box to show an orbital, which is the actual region in space where we're likely to find the electron. And then we show the electrons. Instead of drawing little stick people electrons, we do arrows. So that one arrow is an electron. So that would be one electron in this orbital. If there are two electrons in the same orbital, then the other electron has to spin opposite the first. So this also, another way of saying, so it is the fourth quantum number, the plus 1/2 and the minus 1/2, that for electrons to be together in the same orbital, they have to have opposite spins. But it also means that no two electrons can have the same four quantum numbers. So let me show you what I mean. Let's say we have n equals 2. We're in this S sublevel, and we have two electrons. So we would know that n is 2, L, angular quantum number is 0, which corresponds to the S. The magnetic angular momentum, sorry, did I say magnetic? The angular momentum quantum number, the third one, would be 1, because there's only one way that an S can be in space. It can only be one orientation. And then the last quantum number for one of these electrons is going to be plus 1/2. And then the second electron would have all the same quantum numbers, but the fourth one would make it so that they don't have exactly the same 4. So no two electrons can have the same 4 quantum numbers. That's Pauli exclusion principle, but that then means that in an orbital, remember we're going to use a box to represent that, we can have two electrons, but they would have to be spinning opposite. Let's review this. So this is, you know, we're going to talk about the sublevels, and remember I'm drawing blanks right now. I'm sorry. So we have N is the main energy level, principal. L is the angular quantum number, which tells us the sublevel or shape. And then we have M sub L, which is the angular momentum quantum number, and that's the one that tells us how many ways it can, how many orientations it has. Remember, like the P has 3 ways it can orient itself. I don't know if that's a word. In space, it can be, you know, that dumbbell, it could go in the X, the Y, or the Z coming right at you. So the number of ways that it can be in space is equal to the number of orbitals. So S, remember it's that sphere shape, it can only be one way in the X, Y, Z. So it has one orbital. P, remember that's the one where we would have it, it's hard to show, but you know, like a dumbbell going in the Y, in the X, and in the Z. So it has 3 ways it can be, or 3 orbitals. D I can't draw, but you guys have seen that they have 5 orbitals, and then F has 7. So 7 ways that those F really fancy shapes can be. Some of them are different shape, but some of them are just the same shape but in different directions. So I'm going to go over some more rules about electron configurations, and I promise this is all going to come together. So these are the rules that we're going to use in just a second. When electrons are filling or going in the atom, they're always going to be as low as possible in energy, which means they're going to be as close as possible to the nucleus. So when we write electron configurations, we always start with 1s and then 2s. We don't just all of a sudden start at 5s. So they want to start low and then we fill them. It's kind of like going to like some kind of a concert and you have to go, you know, some people get the front level seats and then you have to go back row by row, but the ones in front are full. The second rule is the one we just talked about, that you can only have 2 electrons. So let's look at like a P. So remember P, there's 3 dumbbells in the X, Y, and Z. So we would have 3 orbitals. And the electrons are going to go, if there are enough, and there are 2 in an orbital, they're going to spin oppositely, which means then that they have, do not have identical 4 quantum numbers. Rule 3, Hund's rule, I also call the bus rule. So remember, well, these cute little kids over here, which I'm in the way right now, but when I remember sitting like 3 in a seat at one point. But anyways, now that you're cool teenagers, you guys tend to, when you do ride a bus, you take your own seats, and then you'll double up if needed. And we're not talking about COVID, because that's a whole new thing, a different thing with busing, but so Hund's rule would be what I was doing up here, I just wasn't explaining it. So let's say that I have a D, let's say I'm talking about like a 5D set of orbitals. So remember D has 5, I didn't mean to cut, that's just by coincidence. Let's make this 4D. So we're in the 4th level away from the nucleus, and we are in a D sublevel. D is that, you know, it's more fancy of a shape, so I can't just describe it with one word. So the Ds have 5, 1, 2, 3, 4, 5 orbitals, or ways that they can be in space. So if I have electrons, these are like you guys on the bus. You're going to all go in your own seat. The electrons will each go in their own orbital. But if there's not enough room, then they'll start to double up, but they will spin oppositely, which is also Pauli exclusion rule. So let me show you this. It's a Aufbau diagram. It's in your book, and we're going to use it a little, and then I'll show you that we won't need to use it, but it is something that can help you to understand electron configurations better. And so what it's showing you is, like, this would be the nucleus down here, and then this would be that if we were believing in rings, you know, like that's the first n equals 1 energy level, and then you have n equals 2, and then n equals 3, and that one gets a little bit messier. And you can see that there's some overlapping here, so let me just show you how it works. So we're going to use those rules I just taught you. Let's do this element. It's on your worksheet. Atomic number 8 is oxygen. And that means we're going to assume it's neutral and have 8 electrons. So I'm going to use this diagram to help me to write out the electron configuration. So I'm going to put 1, 2 of those electrons in this first orbital. So these orbitals are colored boxes. And I need to place all 8 electrons. So those 2 electrons, and I'm filling them from the bottom, lower energy to higher energy. So I'm using Aufbau. I just did Pauli because I spun them oppositely too. So then the next 2 electrons, I'm trying to go to 8, would go here. Again, I'm using Aufbau and Pauli. So there's 4. Then I would go 5, 6, 7. That's Hund's rule. And then 8. Then they would double up. So how would I write that as an electron configuration? I would write it as 1, because in the first main energy level, the S sublevel, I have 2 electrons. So that's what this means. 1s2. Then I go to the next one, 2s2. And then I go here, 2p. There's 2, 3, 4 electrons. So you'll notice that the electrons are going to add to the total number should be 8. When I get to my worksheet, I would just take that answer and I would have written it down here. And then there's another part where they want to know the highest level S and P electrons for the highest quantum number. What they mean is the largest n value. So for this, n equals 2 is the highest, and then any S and P electrons. So like this would be the 2s, and these 3, remember the p has 3 orbitals, this would be the 2p. And then I would just draw in, so I'm really just showing this part now. So I'd have those 2 electrons here, and then I would have these 4. Let's do one more. So let's do one that's a little bit bigger. Atomic number 17, that is chlorine. And then let's do the configuration using this again. So we have 17 electrons. So I'm going to go 1, 2, 3, 4, 5, 6, 7. Hund's rule. 5, 6, wait, no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, Pauli, 13, 14, 15, 16, 17. I know it's hard to read. It's hard. These boxes aren't big enough for me. So that would be an electron configuration of 1s2 for this one, 2s2, 2p6, 3s2, 3p5, and again those add up, those superscripts add up to 17. Over here, I'm only going to show these electrons. So this would be the